Nuclear fission and fusion represent two fundamental processes that harness the energy stored within atomic nuclei, yet they operate through diametrically opposed mechanisms. While fission involves the splitting of heavy atomic nuclei into lighter fragments, fusion entails the merging of light nuclei to form heavier elements. Both processes release vast quantities of energy, but their applications, challenges, and roles in the natural world differ profoundly. This report synthesizes current scientific understanding to provide a detailed comparison of these nuclear phenomena, drawing upon their underlying physics, historical development, technological implementations, and environmental impacts. Nuclear fission occurs when a heavy, unstable nucleus such as uranium-235 absorbs a neutron, becoming uranium-236. This temporary isotope rapidly splits into two smaller nuclei, for example krypton-89 and barium-144, while releasing additional neutrons and energy. The process is initiated by neutron bombardment and sustained through chain reactions, where the emitted neutrons induce subsequent fissions. This self-propagating reaction forms the basis for nuclear reactors, where control rods moderate neutron flux to maintain a stable energy output. The energy released during fission arises from the conversion of nuclear binding energy into kinetic energy of the fission fragments. While this per-atom energy seems minuscule, the Avogadro scale quantities in nuclear fuel enable substantial power generation. Fusion requires overcoming immense electrostatic repulsion between nuclei, necessitating extreme conditions unattainable in terrestrial environments without advanced confinement technologies. The Lawson criterion quantifies the necessary combination of plasma density, temperature, and confinement time for net energy gain, parameters that remain challenging to achieve consistently in experimental reactors. The energy disparity between fusion and fission stems from differences in mass-to-energy conversion efficiency. Fusion reactions convert approximately 0.7% of the reactant mass into energy, compared to 0.1% for fission. This translates to fusion producing 3.4 times more energy per unit mass of fuel. However, the energy input required to initiate fusion vastly exceeds that for fission. Fission reactors operate at near ambient temperatures using slow neutrons, while fusion demands heating fuels to plasma states exceeding 100 million Kelvin, a temperature regime where no material containment is feasible, necessitating magnetic or inertial confinement. This paradox of high activation energy versus greater output remains the central challenge in fusion energy development. Natural fission occurs sporadically in uranium deposits, such as the Oklo natural nuclear reactors in Gabon, where geological conditions moderated neutron fluxes 2 billion years ago. However, sustained fission chain reactions require precise human-engineered conditions. Modern nuclear reactors utilize enriched uranium-235 in controlled criticality states, where delayed neutrons enable safe power modulation. The Chernobyl and Fukushima accidents underscore the risks of losing control over these chain reactions, which can lead to catastrophic meltdowns and radiation release. Fission's military application materialized in 1945 with the detonation of uranium and plutonium-based atomic bombs, which rely on rapid, uncontrolled chain reactions. Stars sustain fusion through gravitational confinement, balancing radiation pressure against gravitational collapse. The proton-proton chain dominates in Sun-like stars, while massive stars employ the CNO cycle. On Earth, magnetic confinement fusion and inertial confinement represent leading experimental approaches. The ITER project in France aims to demonstrate 500 MeV fusion output from 50 MeV input by 2035, leveraging superconducting magnets to confine deuterium-tritium plasma. Thermonuclear weapons artificially replicate stellar fusion conditions using fission explosions to compress and heat fusion fuel. The 1952 Ivy Mike test demonstrated fusion's destructive potential, releasing energy equivalent to 10.4 million tons of TNT. Fission generates long-lived radioactive isotopes like cesium-137 and strontium-90, requiring secure geological storage for millennia. High-level waste from reactor cores emits intense gamma radiation, necessitating shielded containment. In contrast, fusion primarily produces helium and short-lived neutrons, with reactor components becoming mildly radioactive from neutron activation, a more manageable waste profile. Fission reactors risk meltdowns due to cooling system failures, as evidenced by the 1986 Chernobyl disaster that released 5,300 pbq of radioactivity. Fusion reactors, lacking chain reactions, cannot experience uncontrolled power surges. However, tritium handling poses biological risks due to its V-emitting properties and ability to replace hydrogen in water molecules. From a proliferation standpoint, fusion plants would not produce weapons-usable materials, unlike uranium enrichment or plutonium breeding in fission cycles. Generation FU fission reactors aim to improve sustainability and safety through designs like sodium-cooled fast reactors and molten salt reactors. These systems promise to utilize 99% of uranium fuel and operate at atmospheric pressure to reduce accident risks. Small modular reactors under 300 MW capacity offer grid flexibility and reduced capital costs. Achieving ignition, where fusion self-heating sustains the reaction, remains elusive. Key challenges include plasma instability mitigation, materials resistant to neutron embrittlement, and efficient tritium breeding. Recent advances in high-temperature superconductors and laser compression suggest progress toward break-even. Commercial viability likely requires sustained confinement times exceeding 1 hour and tritium breeding ratios above 1.1. Nuclear fission and fusion present complementary advantages and challenges within the energy landscape. Fission offers a mature, albeit waste-intensive power source, while fusion promises abundant energy with minimal environmental impact if confinement and fuel cycle hurdles can be overcome. The development of hybrid fission-fusion systems may bridge this technological gap, utilizing fusion neutrons to transmute fission waste or breed fissile fuels. As climate change accelerates, understanding these nuclear processes becomes critical for shaping sustainable energy policies that balance safety, proliferation risks, and decarbonization imperatives.